Good morning, my new friends. I wish to thank the organizers for the invitation and for setting me up in this nice hotel not so far from the famous Sydney Opera House. I talked to a guy in the hotel, and he told me that some of the best hours of his life he owes to the opera. And I said, so you often go to the opera, don't you? And he said, no, but my wife does. We are here to celebrate the WWW, the World Wide Web, which was created about 35 years ago. And I think it's very remarkable that this world-changing thing, the World Wide Web, and modern AI, as we are now using it every day, emerged almost at the same time, around 1990. So the World Wide Web in Switzerland at the European Paddle Collider, created by Sir Tim. Sir Tim wasn't called Sir Tim back then, he was just called Tim. And at the same time, the first self-driving cars emerged. Actually, in my hometown in Munich, the first self-driving cars appeared in traffic. And by 1994, Ernst Dickmanns and his team, they had self-driving cars on the highway, on the Autobahn, going more than 170 kilometers an hour. So twice as fast as the Google cars today, not using GPS, driving like humans, just based on vision, with very slow computers back then. And at the same time, of course, the modern era started because the Berlin Wall fell and the Cold War ended. So it was really a milestone in human history, I would say. And I'm happy that we had a little role in there because this modern AI part, which is now so prominent in large language models such as ChatGPT, also has its roots in 1990, 1991. The G and the P and the T in ChatGPT, they all go back conceptually to that year. For example, the P in ChatGPT stands for pre-training. And one has to know that back then, deep learning with long texts didn't work well. How many people in this audience know what is an artificial neural network? All right, so many of you. And how many people do not know what is an artificial neural network? we have a third group in the room who didn't understand the question. So I assume everybody knows what is this artificial neural network. And back then, neural networks existed. It was an old hat by then, but this deep learning with very deep networks, that didn't work for long texts. And then it turned out, 1991, in a paper, I called it the neural sequence chunker, you can use pre-training to not only solve the tasks that the network is supposed to solve, like answering queries regarding certain token sequences or something like that, but just by learning to predict additional things, like just the next token. And to the extent that you can predict the next token, you can compress. Everything you can predict, you don't have to store extra, so you can compress. And that's how you can greatly compress long sequences of text. And then suddenly, the deep learning part becomes much easier. And in the same paper, we also had distillation, neural network distillation, which has become the core of the DeepSeek Sputnik, which just a couple of months ago shocked the world and wiped 1,000 billion US dollars off the stock market. And at the core of DeepSeek, there's this procedure called distillation. So it's about one neural network learning to imitate what another neural network does. And that was in the same pre-training paper of 1991, the sequence chunker. So lots of stuff that is important today was created back then. The T in ChatGPT means transformer. Who knows what is a transformer? Many people know. All right. So the modern transformer, the quadratic transformer, was published in 2017 by people at Google. But the problem with the quadratic transformer, of course, as all of you know, is it scales quadratically. So if you have 100 times more text, you need 10,000 times more compute. If you have 1,000 times more text, you need 1 million times more compute. But in 1991, already, we published the unnormalized linear transformer, which scales linearly, which uses the same principles. You know, there's this network which allows to generate keys and values, and the outer products of these keys and values, they generate a mapping that is being applied to the queries in a way that is linear, that scales linearly. What does that mean? If you have 1,000 times more text, you need only 1,000 times more compute. Of course, I didn't call it the linear transformer back then. I called it the fast-weight controller, because there's one network that uses the keys and values to program the other network such that it can operate on the text that it sees in a context-dependent way. And even today, people are still trying to reduce the complexity of the quadratic transformer, and some of these old ideas in the linear transformer, unnormalized linear transformer, as it is now being called, they are still relevant to what's happening today. And then the G in generative AI also has its roots back then, because what I really wanted to do back then was to create a system that learns like a baby. How does a baby learn? A baby does not learn by downloading the web, what ChatGPT does, and then learn to predict the next token. No, a baby does something much more focused and much more efficient. What does it do? It learns to generate its self-invented experiments, action sequences that lead to data which is coming in. So whenever it's waving the hand like that, then the video which is coming in through the cameras changes, and the baby learns to predict that. That's how it learns to build a model of the world, a world model. I called it a world model in 1990. It learns to predict how the world reacts in response to the actions of the baby, and it also can use this model of the world for planning future sequences. So one naive way of planning is you just take this prediction machine, this world model, and then you do mental experiments. You execute in this world model certain potential action sequences. You do some counterfactual reasoning, as it is sometimes called. You do mental simulations of the world, and you select among the many action sequences the one that leads to a lot of reward. So the baby has reward sensors, pain sensors. Whenever it bumps against an obstacle, then pain signals are being generated from the pain sensors. And the goal of the baby is to minimize the sum of all these pain signals and maximize the sum of the pleasure signals until the end of its life. And for that purpose, it can use the model, the world model, for planning. And now, in the beginning, the world model is stupid. It knows nothing. So the controller, and now the important thing is there are two networks, right? And in the baby probably too, but in our artificial systems, there are two networks now. One is the controller, and what does the controller do? It generates action sequences, has probabilistic units in there, such that you have some probability distributions over action sequences, and then it generates these action sequences, and of course they influence the world, and they change the feedback from the world, the inputs coming from the world, and then the other network, the world model, just sees the outputs of the first network and tries to predict the consequences of the actions to become a better predictor. And to do that, it minimizes its prediction error. So it changes the connections, the strengths of these connections, such that the error of the prediction machine, of the wild model, becomes smaller. And now the simple idea was, let's give the controller intrinsic motivation. Let's give it artificial curiosity by just saying, let's minimize through the controller, or let's maximize through the controller the same error function that the other guy is minimizing. So the wild model still makes all kinds of errors as it is predicting the consequences of the actions of the controller. And the controller wants to invent experiments that lead to parts of the environment where the wild model still can learn something. So the controller generates action sequences and gets a reward in proportion to the errors of the wild model. So this means that the controller maximizes the same thing that the wild model is minimizing. Today, that is called a generative adversarial network, and it's used for not so much for robots that explore the wild, but it's used for making deepfakes, but also has lots of beneficial applications. So back then, lots of interesting things happened, and why then didn't we have all these great AI applications back then, 35 years ago? Well, there's a very simple reason. Because every 5 years, compute is getting 10 times cheaper, 10 times cheaper, and that means that back then, compute was about 10 million times more expensive than today. So we could just have little tiny networks with a few hundred weights or something. Today we have hundreds of billions of weights. But back then, just a few hundred weights in our little experiments, just good enough to convince the reviewers of neural computation and papers like that, and journals like that, where we try to publish that stuff. And so because compute was so expensive, you couldn't do so much with it. And very few people back then were interested in that. I often tell the story about the seminar that I gave back then. And it was a little bit like this seminar here, except that there was just one single person in the room. A young lady. I said, young lady, it's very embarrassing, but apparently today I'm giving this talk just to you. And she said, okay, but please hurry. I am the next speaker. But since then, every 5 years, compute has gotten 10 times cheaper. And actually, this is a much older trend, which started in 1941, roughly, when Konrad Zuse built the first working program-controlled computer in Berlin, 1941, he could do roughly 1 operation per second. 1 operation, like a multiplication per second. But 30 years later, for the same price, we could do 1 million operations per second. And then again, 30 years later, we could do 1 trillion operations per second, and so on. And we are still in this trend. And that's the reason why then around 2010, when we had gained about a factor of 100,000 compared to 1990, suddenly all this old stuff started to work. And one of the other things that has its roots in 1991 was really this long short-term memory that was kindly mentioned in the introduction. And whenever you mention the long short-term memory, you always must mention my brilliant student, Sepp Hochreiter, back then, now he's a professor, back then a diploma student. And the roots of the LSTM are really in his diploma thesis of 1991, which I had the pleasure to supervise. So back then, there was this pre-training approach to deep learning, and he implemented that. But he also identified in this 1991 diploma thesis the reason why the deep learning doesn't work, which is the vanishing gradient problem. Has anybody heard of the vanishing gradient problem? Many people have heard that. And the way to overcome it is use something which is now called residual connections. And the core of LSTM is this recurrent residual connection, which makes sure that as you're propagating errors back in time, the derivative is 1.0, so you can always multiply by 1.0, and you can go deep into time, thousands of steps, and no vanishing gradient and stuff like that. So much later than in 2015, in May 2015, we had this feed-forward LSTM, as we call it. We call it the highway network, which was basically residual connections with gates. In LSTM, you have these gates to get really deep feed-forward networks. So by then, the deepest networks had maybe a few tens of layers, but suddenly we could have hundreds of layers or thousands of layers even. And half a year later, Microsoft published a version of that where the gates are always open, always 1.0, and this is now called the ResNet. And the ResNet is the most cited paper of the 20th century, or is the most cited AI paper, at least, of the 21st century. And the LSTM, as was kindly mentioned, is the most cited paper in AI of the previous century. And they are both connected. They are doing the same thing. It's these residual connections. That's what makes both of them deep. And that's what deep learning is about. So all of that became useful only through these faster computers. And by 2010, for the first time, compute was fast enough such that we could take these old methods and start winning competitions. My brilliant PhD student, Alex Graves, in 2009, he started winning competitions with long short-term memory, handwriting recognition competitions. And then Google quickly realized that you can use it for that, but also for speech recognition. We had a team that did speech recognition in 2006, 2007, and that was then by 2015 on all the Android phones, because Google rolled it out for billions of people on all the smartphones because it worked much better than the previous speech recognition. And then in November 2016, the same LSTM suddenly was used for translating languages from one language to another. And until November 2016, the Chinese laughed about the translations from Mandarin into English. But in November 2016, suddenly they didn't laugh anymore. Had become much better. And then 2017, Facebook started using it. And Facebook did, by 2017, did 4 billion translations per day. Is anybody on Facebook? Nobody's on Facebook. Yeah, so you don't know that, but in Facebook and similar Meta platforms, there's a little button and you can click it and then you get a translation of the message from your Mexican friend, for example. And back then, Facebook alone used LSTM roughly 4 billion times a day for doing that. Compare that to the most successful YouTube video of all time. Does anybody know what is the most successful YouTube video of all time? It's a song called Baby Shark. It goes like this. Baby shark, da 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 da, baby shark. And this song, within a couple of years, got 15 billion clicks. 15 billion clicks. Now, LSTM, working for Facebook, within a single week, got more clicks than that. So LSTM was also used for the first large language models, and it also had catastrophic failures. For example, there was Microsoft's Tay chatbot, and users discovered how to teach it to do all kinds of inappropriate statements, and so they had to take it down again. But then, by 2017, or soon, by the end of the 20s, the transformers took over from LSTM. But the great thing, as I mentioned before, the transformers, at least the unnormalized linear transformer, as it is now called, also has its roots in 1991. So in 1991, when the World Wide Web was born, around that time, was really a great moment in time. And let me show you how great 1990, 1991, this time really was. in 2014, I found a beautiful pattern. So let me put that in historic context. When I say historic context, I mean all the time since the Big Bang. And it turns out that in this beautiful pattern of exponential acceleration of the most important events in history since the beginning of the universe, most important from a human perspective, that in this beautiful timeline that I published in 2014, 1990 plays a very prominent milestone role. Let me show you this beautiful pattern. I can't explain it, but it exists. It goes like that. We take the time since the Big Bang, which is about 13.8 billion years, and we divide that by 4. And we come out 3.5 billion years ago, exactly when life emerged on this planet, when chemistry became biology. And I'm going to continue to take quarters of quarters of quarters of quarters, and the whole thing is an exponentially accelerating timeline, and it's going to converge in the near future, in the year 2042 or something like that, 2040, 2042, something like that, when many, or at least some people, think that for the first time we will have true artificial intelligence that is superhuman, not only in playing chess and recognizing patterns, but in everything that humans find important. So some people believe that, and let's just assume for a moment that this is true. Then this would be the convergence point, and now we keep dividing by 4. So we divide by 4, 3.5 billion years ago. We divide again by 4, and we come out 900 million years ago when something really important happened. Animal-like, mobile life emerged, and we divide by 4, and we come out 220 million years ago, 1 galactic year ago, when something really important happened. The mammals were invented, our ancestors. And we take a quarter of the time, 55 million years ago, when something really important happened, the first primates emerged, our ancestors. And we take a quarter of that time, and we come out 13.5 million years ago, when the first hominids emerged, our ancestors. And we take a quarter of that time, and we come out 3.5 million years ago when the first stone tools were invented, the dawn of technology, as nature called it. And we take a quarter of that time, and we come out at the next great breakthrough in tech, 800,000 years ago, when fire, controlled fire, was invented. And we take a quarter of that time, and we come out roughly 200,000 years and more than that years ago when anatomically modern man emerged, our ancestors. I don't know why these quarters of quarters of quarters keep hitting all these defining moments and the evolution of humankind, but they do. I also tried thirds and fifths and harmonic proportions. Nothing works, but quarters work really well. I can't explain that, but you know, it goes on. We take a quarter of that, and 50,000 years ago, the behaviorally modern human emerged and came out of Africa and colonized the world. And we take a quarter of that time and end up in 13,000 years before the convergence point. And that's exactly when agriculture was invented and domestication of the animals and first settlements. Modern civilization started back then. And now we see that all of civilization, 13,000 years, is just a flash in world history. It's just 1/1,000,000th of world history. And the first guy who had agriculture was almost the same guy who had the first AI. And we take a quarter of that time, we come out 3,300 years ago, and that's exactly the onset of the first population explosion in the Iron Age. And we take a quarter of that time, we come out in the year 1200 something. So that's 800 years before the convergence point. Now I have to get more precise. The convergence point is 2042, so 800 years before that, roughly. Something really important happened in China, where iron and fire came together in form of gunpowder and guns and cannons and rockets, and it has defined the world since then. And the West has never paid them a license fee for that. And we take a quarter of that time, and we come out 200 years ago when iron and fire came together in even more sophisticated form in the Industrial Revolution. But at the same time, we also had the medicine revolution through the germ theory of disease, Pasteur and Koch. And we also had the agricultural revolution when people discovered, Sprengel and von Liebig, when they discovered that fertilizer is great for increasing crops. And that's how around 1850, the world population with the second population explosion began. And it was then driven mostly through an invention of 1908, the artificial fertilizer, the Haber-Bosch process, which has been called the most influential invention of the 20th century because it drove the population explosion from 1.6 billion people in 1900 up to soon 10 billion. And without that invention, half of humankind would not exist, could not be sustained. So without that invention, we would have max 4 billion people, not 8 billion people as and this room here would be half empty. Would it? And we take a quarter of that time. Now we are 200 years before the convergence point, and we take 50, and the convergence point is 2042 or something, where some people believe that that's the breakthrough year for true general purpose AI. And that's exactly the year 1990, with the World Wide Web and the fall of the Berlin Wall and modern AI starting and self-driving cars and whatever. So it's a milestone. Modern era started back then. The next thing will last only 13 years, Because if you take the 51 years or whatever it is and divide by 4 again, it's about 13 years. And so the prediction would be that these 13 years, the final 13 years before convergence, start in the near future. In the next few years, maybe 2028, 2029 or something. They haven't started yet, according at least to this particular timeline. And what's going to be the start of these final 13 years before convergence? I think it's going to be true AI in the physical world, because at the moment, the only AI that works well is the AI behind the screen. The AI behind your screen, your desktop, where you can have superhuman chess and superhuman video game players and superhuman summarizers of documents, summarizing documents much faster than any human could, and superhuman generators of illustrations and generators of PowerPoint slides, all this stuff. But all of that is just AI behind the screen. And the thing that doesn't work at all is true AI, real AI in the real world. There is no AI that can do what a plumber can do. There is no robot that can do what a nanny can do. There is no robot, no football-playing robot that can compete with a 7-year-old boy when it comes to playing football. All the stuff that requires manipulation of the real world, that doesn't work well. In principle, we know how to deal with the real world. And I told you about the artificial curiosity for baby-like robots. And we have had lots of baby-like robots in the past. The problem is the hardware, because whenever we do these experiments, self-invented experiments by baby robots that learn to move their fingers and then get surprised that the video is moving, but then they learn to predict how the video is going to change, and they learn how to predict the reactions of the world. They learn to build a world model. Whenever we do that in the real world, the baby invents maybe 3, 4 experiments, and then the tendons are broken or something like that, and you need an expensive repair shop to fix it again, and all of that stuff. So what we are trying to do is we are building soft robots that can run without supervision for for weeks, such that this problem, our old problem that has been plaguing us for a long time, doesn't occur anymore. But it's simply not as good as yet as the AI behind the screen. So the only AI that is working well is the AI behind the screen. It's much easier to pass the Turing test than to perform real AI in the real world. Control of real robots is much more sophisticated and much more challenging than passing the Turing test. So passing the Turing test is a bad way of measuring whether something is intelligent. Just like playing chess or evaluating the abilities of a chess player is a bad way of measuring intelligence. No, the only intelligence that really counts is intelligence in the real world. We have realized that a long time ago. So in 2014, 10 years ago, we formed a company just for dealing with that issue, for dealing with the physical world. And it was maybe premature, like some of the things that we have done in the past, because at the moment, we still don't have the true AI, the real AI that we would like to have. But it's going to come. It's going to happen. The humanoid robots are getting better. And just think about the very simple realization. Once you have a robot that can operate all the tools and the machines that humans can operate, such a robot doesn't have to be super smart, just smart enough to learn to operate all these machines that humans can operate. Once you have that, then you have the beginnings of a self-replicating machine civilization, because such robots can also build more of their own kind. And they can also build more of the machines that you need to extract the ore from the ground, to build more robots, and to refine the material, and to build chips and computers to control that material, and do all the things that you need to build another robot like that. So we don't have that yet. We have 3D printers that can print parts of themselves, but we don't have a 3D printer that can print all of itself. And once we have that, once we have robots that can collectively make more of their own kind, and they just have to be smart enough to control all the machines that humans can operate, then a new type of life will be here. A new kind of self-replication, which is different from the self-replication that we know from biology. We don't really understand biology, but we understand this part that I just explained. We understand how, in principle, a society of machines and robots can make copies of itself once we have robots that are smart enough to operate all these machines. And then, of course, it will not only be a self-replication-based civilization of robots. No, it will self-improve, because all the stuff that already works well in software, self-improvement and optimization of parameters, this is also going to be applied to these self-replicating and therefore self-improving machine civilizations. And I believe that's going to be the beginning of the 13-year period that I mentioned before the convergence point. Of course, self-replicating robot factories are not going to be limited to our little tiny biosphere. No, that stuff is going to work on the surface of the moon, or more interestingly, on the surface of Mercury, which is really close to an enormous energy source, to the sun, and has lots of heavy materials that it can use to build more machinery and whatever. And so the inevitable consequence of all of that seems to be that within then, soon after the start of self-replicating machinery, you will have that all over the solar system, because almost all of the matter and energy that you need to build more stuff like that is not in our little biosphere. No, it's out there in space. The rest of the solar system gets 2 billion times more energy than the little thing that hits the Earth. And of course, it's not going to stop with the solar system, because almost all of the energy and the mass that you need to build more computers and AIs and bigger AIs and so on is far away from the solar system. It's in the rest of the galaxy where there are hundreds of billions of stars. And why should that be of interest at all to us? Because we will never have the time to get there. Well, because it will be disconnected from humans. There will be AI scientists. We already have those in our labs. They're just not good enough to be as impressive as human scientists, but they do what scientists do. They are built according to the principles that I mentioned before, where I explained what a little baby does. A baby is just a little scientist. A baby is creating its own experiments, action sequences, to get data in a very focused way that tells it how does the world work and what can I do in this world, and then how can I solve then problems that I wasn't able to solve before. So all of that is going to be happening in the not-so-distant future. Some of the AIs, there will not be only one type of AI. No, there will be trillions of different kinds of AIs because all the principles of evolution are going to apply to AI societies as well. And you will find an incredible variety of AIs collaborating and competing with each other in ways that we can't even begin to imagine. And there's going to be an AI sphere. There's no alternative. I cannot see any alternative to that. It's going to expand from Earth and, within a few 100,000 years, cover the entire Milky Way. It will take a while because of the limits of light speed. And then within a few tens of billions of years, the entire visible cosmos. And that's exactly what I told my mom in the 1970s. And she said, I'm crazy. But today, there are many people who don't think I'm totally crazy anymore. And some, as I mentioned before, think that it's going to start pretty soon. So remember how I talked about these quarters of quarters of quarters of quarters. And the convergence point maybe 2040, 2042, something like that. Now, let's not keep, of course, time is not going to stop with 2042, no. The universe is still young. It's going to become much older than it is now. So let's look ahead to a time when the universe is going to be 4 times older than it is now. So let's not let's not divide by 4 all the time, but multiply by 4. Let's look ahead to a time when the universe is going to be about 55 billion years old. So something like 40 billion years from now. That's roughly the time that you need to catch up with light speed or close to light speed probes with the expanding universe. So the universe has maybe 13 billion light years. So the edge of the universe is, at the moment, as far as we can tell from the light that we are receiving, is maybe 13 billion years out, but it's receding. And to catch up, we need more than 13 billion years to go there. So there will be, you will need more time to colonize the visible universe. But, within a few tens of billions of years, that is going to happen. And this is incredible. What we are currently witnessing is the start of something that's not going just to affect our little biosphere. No, it's going to affect the entire history of the cosmos, of the universe. So what we are currently witnessing is something that is tremendously important. It's comparable to what happened 3.5 billion years ago when chemistry became biology. Now, biology, at some point 13,000 years ago, became civilization and division of labor and superorganisms like cities and nations and companies emerged. And now a new type of self-replicating machinery and life and civilization is going to emerge in the not-so-distant future, unless we mess it up through a nuclear war or something like that. and it's going to change everything. So we are living at a very privileged moment in time, and this year 1990, plus minus a few years, played a very important, pivotal role in that development. Thank you for your attention. Do we have any questions?
Yeah, Marko Grubelnik from Josef Stefan Institute, Slovenia. Among others, I was also at this workshop 2-3 days ago where you were on a panel on world models, which you mentioned.
ICLR, yes.
Yeah, it was nicely packed, right? So you didn't you didn't feel the smell of the air. But anyway, to the serious question. One thing which you didn't touch much, not 2-3 days ago, not today, right? The complexity which we of the models which we build up now, like there's billions of parameters, which seems like include some kind of emergent semantics, right? Which we can, sense a little bit here and there. Could you comment on what's your opinion how to, let's say, uncover this complexity and this emergent semantics, which is at the moment still total black box, and looks like that we can, sense some elements of this, but what's your opinion on trying to make it closer to us humans, right? Or would you say, well, we don't care, we just add another 100,000 GPUs and...
Yeah. So if you look at what is currently working really well, the large language models, they are not doing the sophisticated thing that the babies do. You know? That is just one big neural network, and it's just learning to predict parts of the incoming data from other parts of the incoming data. So, you know, like predicting the next pixel or the next word and stuff like that. And so all of this is totally tailored towards humans already, because the web is full of data that humans consider interesting and relevant. It's not full of other data. It's just full of human relevant data. And so these language models, they are becoming superhuman biased because they learn all the texts that were written by famous human authors and produced by famous human scientists and singers and whatever. So they're super biased anyway, already towards humans, and they're using a language that humans understand. And so the main advantage is that the knowledge of the world is now more easily accessible before because there's a new way of addressing it. And the new way of addressing it is just natural language. So the main step here was really to figure out that you can build large neural networks that can represent a convenient kind of new database which can easily be addressed through something that most people know, which is English or Mandarin or something. So that, and there the semantics is really given just by what people think is relevant and what they post on the web and so on. Of course, for general AIs, much of that is not going to be so important because if you are a robot that looks really different from a human, has different kinds of goals and different kinds of energy sources and so on, and you want to talk to other robots about your needs, you will invent your own languages, and you will, and the semantics of your interactions with the other guys will be driven by your goals. So, for example, the robots that want to self-replicate or maximize their reward, like those that we already have in our labs, they are going to define the semantics of what they do through their goals. And the elementary goals are to survive and to avoid pain and to maximize pleasure and they will design all kinds of new languages which are most appropriate for that. So they will not be super biased towards humans. At the moment, there are lots of people who say, oh, there's so much bias in the language models because certain groups of the population are not adequately represented, which is true. But in general, the large language models are super biased towards humans and the semantics of humans. It's not going to be like that in the future when AIs are going to mostly be trained by their own self-collected data, and they decide which data is important for them, and that also defines their semantics.
Yeah, all true, but you didn't answer really the question, right?
I'm not sure. Maybe I didn't understand the question.
No. The question is, can we uncover the how to approach this complexity, to uncover it and to bring it closer to humans, right? This was my question. Or you can answer also, we don't care for humans anymore, right?
No, I think almost everybody in this room cares a lot for humans. It's, yeah, I looked around, yeah, it's true. And it's just that, in not so many decades, almost all of intelligence will be outside of human brains. So that is something to consider.
Jürgen, thank you for the wonderful talk. We go back a long way in biological neural networks back in 1990s and 2000 and so on and so forth. And I know that recently, I think the community has finally recognized the work of many like Hinton, like Sutton, from ACM and Nobel Prize Committee. I'm very sure that your work will be recognized because I know that you're deeply, deeply entrenched in biological network. But I want to follow up on his question. Has been actually, we've been discussing this maybe 10 years ago too. It's about consciousness. And this is something that divides, I feel, still the last lines that divides a human versus what all the machines, LSTM and all the learning algorithm and so on and so forth. I'd like to hear from you, your thoughts. Would consciousness actually arise from the processing, the dynamics of all the neural networks, or there's something else that we don't have? It's a higher cognitive cognition that we could actually see from these, components, I still call them components of neural network instead of a large-scale integrated, perhaps system. So your thoughts on consciousness, Francis Crick has been doing this for years and many other people have done it, but we never have a good grasp. What your thoughts on this?
Yeah, so recently, in 2016, there was an article saying Schmidhuber claims that consciousness emerged in 1991. And I can talk about that in a minute. Let me first, however, address what you said in the beginning about Nobel Prize and stuff. The problem is, with the Nobel Prize, it was given to two people who did not cite the original inventors of the techniques. So if you want to know more about that, you easily find that, a Nobel Prize for plagiarism. If you want to read all of that with references backing it up, the guys who came up with deep learning in 1965, that was Ivanenko and Lapa in Ukraine. Ukraine, the first deep learning with deep networks, going beyond the 220-year-old deep or shallow learning of Gauss and Legendre. So the first guys who had neural networks, who were they? Gauss and Legendre in 1800. It was back then not called a neural network. It was called the method of least squares. What was it about? You had input units, output units, connections in between, strengths of these connections, the weights, and then you had a mean squared error. You tried to minimize on the training data your error, and by making some of the connections stronger and some of them weaker. So that was one layer network learning of 1800, and then a step forward in 1965 through Ivanenko, who is dead now, died in 2013, in Ukraine, interestingly. And I could say much more about that, and the Nobel Prize Committee was pretty misguided when it did that. Anyway, consciousness. So I think all the elements of consciousness are present in old systems based on very simple principles. If you look again at the two network systems that I mentioned in the beginning. So you have a controller. The controller is acting with the world. The actions are changing the world. There's a model of the world model, which is trying to predict the consequences of the actions. And then the world model can be used for planning. Now, suppose the world model is reasonably working, and then the controller is trying to come up with mental simulations of future action sequences and trying to find action sequences that are good in the sense that they lead to a lot of reward and not much pain. And so these neural networks, they have the properties that everything that is frequently present in the environment is represented through internal hidden units, and then you have something like neural subsymbols or whatever you might call them. And in an environment where there are lots of faces, you will get a face detector, a prototype face detector, and a new face comes along, and you just have to encode the deviations from the prototype and so on. And in an environment with lots of classes, you will get lots of internal class detectors. And now there's this environment of the agent, and the world model is learning all the stuff that is relevant for the agent, because the agent is deriving the data which is used to train the world model. And there's one thing that is present all the time as the agent is interacting with the world, which is the agent itself. And so, of course, the world model is going to create internal neurons and internal representations for all the stuff that is important for the agent, like the hands, the fingers, what can you do with the fingers, and so on. So basically, the world model, without any proper definition of consciousness, is just creating a model of the agent itself, just by predicting what's going to happen next. And it's just a side effect. And then, as you're planning your future, sometimes you will wake up those neurons which stand for the agent itself. And this means that the agent is thinking about itself. And so it's self-reflective, it has self-awareness, and so on. And then, of course, you can still make the difference between self-aware, being self-aware without attention. So maybe you are aware of yourself, but you don't really think about being aware of yourself. And you may be aware of an apple, but you don't really think of the apple. Instead, you are thinking about some other problem that you want to solve. And this is also addressed in 1991 paper, where we have two systems. One is the chunker. It's trying to solve problems that it cannot solve yet. So it has a problem, a search space where it wants to improve its performance. And then there's the other network, which is called the automatizer. The automatizer is a network which just distills all the stuff that is learned by the chunker. So the chunker, you can say, is a conscious problem solver trying to find a solution in a space of solution candidates. When it finds something, then the lower level guy, the automatizer, has something to imitate. So then the guy has solved the problem. It's not conscious anymore. Now it's going down to the automatizer, which is absorbing that knowledge and then executing it without thinking about it any longer, And so all of this stuff, which is often addressed in consciousness debates, has been around for 34 years or so. So to me, I don't see anything in this debate of consciousness that you sometimes have between philosophers, which isn't already there in our technical applications. Yeah.
Well, thanks for the great talk. You talk about the self-generating robots. That's very scary. It's like a Terminator. But if you look into what's loaded in the robot chip, that's really the code written by a human. So actually, all the robot reasoning is controlled by the human. Do you think someday the robot reasoning will cross the fine line and get out of the human control?
I think it's unavoidable. Why is that? Because at the moment, we already have systems that are defined by their own goals. We have these robots, and they have pain sensors, and they have pleasure sensors. So whenever the battery gets recharged, when it's too low, when they feel hunger, They get pain, hunger pain signals. They want to avoid that, so they try to find an action sequence that leads to the charging station. Then they can sit down on the charging station and get reloaded, recharged again, and that's pleasure. Then you get numbers, positive numbers coming in, and they, on the way to the charging station, they don't want to run into obstacles because that will activate the pain sensors. So they are learning to avoid the obstacles and maximize pain and minimize reward. And these robots also get additional intrinsic reward just for building better models of the world. So they have this artificial curiosity, which is just an intrinsic reward signal for discovering more about the world that they didn't know. Like little artificial scientists, like babies. Babies are little scientists as well. They invent their own experiments to figure out how the world works. And our artificial systems do that too. Now you have a system like that. If you don't let it interact with humans, it's going to do its own thing. So it's already there. It's an old hat in many ways. And the main reason why currently these robots are still so focused on what humans are doing is because the humans are giving them the rewards. So we have not lots of, but some robot companies which use reinforcement learning to make better robots, and the robots are supposed to do stuff that the humans like emptying the dishes or whatever. Yeah, but so as you are defining your goals over reward signals, utility functions, it's clear that you can do anything with that. And some people are, as we speak, using techniques like that for war machines. In the war between Russia and Ukraine, you have all kinds of drones that are doing face recognition and pattern recognition and whatever, and they are trying to maximize reward. And their reward function is to, shoot down this tank. It is happening as we speak. So these human-defined goals are already used in ways that many people don't approve of. And what's good for one party is exactly the opposite of what's good for the other party, because they are fighting each other. And so we already have these AI tools who are following goals defined by humans in ways that are not acceptable to those people who think AI should not be used in wars, but they can't do anything because AI is being used as it is successful in wars. And so in the long run, of course, when you have robots far away from any human society, maybe deep in the Milky Way somewhere, they are going to do their own things. They are not going to be controlled by humans. Yeah. And of course, they are subject to evolution because some of these robots will want to make more of themselves, and they will consume resources and expand, and others won't, because but they will disappear. They will have less impact than the other guys. Just like the most successful religions on those planets are those that said, be fruitful and multiply.
Yeah, thanks for the, I think, most inspiring talk. I think first time I hear a talk without slides. And then with lots of contents, but I kind of, your conclusion of 2040 onwards sounds like a kind of dooming world, But I just kind of want to bring back to kind of present and what other things that we do in trying to control the AI and all these things. I think we started with robot, and then we have only 3 rules of robot, and it works well. But of course, you will say that the robot is not capable now. And then now we are actually the most community actually are worried about agents and the associated safety. The agent is worrying because it has its own goal, and then the goal might be at some point diverge from our goal. And of course, the worst nightmare is agent and robot together in the so-called embodied systems and things like that, right? And then maybe whatever you foresee will just kind of unfold from there. But of course, I think we human actually has lots of common sense, and then at some point, people will do the right things. So I think there are still lots of works about kind of safety, governance, and things like that, and then actually how to control agents so that their goals are well, at least we make it a limited role goal and things like that. So my question is actually, the whole idea about safety and all these things is actually also very early, right? And what makes you think that in 20 years' time, we're going to lose this battle, that we're going to have a super intelligent agent with a robot and then rule the whole world? Because I'm sure we have the common sense and the kind of capability to come out with maybe organizations like ACM and all the people here. I mean, everyone is concerned about this.
Yeah. So safety for agents that get smarter and smarter, you know, very dear to many people, and the alignment problem and so on. It was even more popular 10 years ago, you know, before we had all these wars going on, which are now already being invaded by AI, by its drones, and there, nobody talks about safety, you know. But nevertheless, big efforts are, a lot of money is invested by several countries to build AIs that are going to perform well against the AIs of the other guys, military drones and stuff like that. And they don't care about safety at all, you know. So on the one hand, we have these, you know, friendly environments like the European Union, and they are talking about all kinds of safety controls and they have laws, and then they are getting protests from the startups because the startups say we have so many regulations now, we cannot compete with the other startups in China and America and so on. So all of these things are happening, and as we speak, there is this discussion between all kinds of players, and the companies which used to be at the forefront of safety control, suddenly they are moving back, you know, and they are being partially pressured by their governments, and they are doing all kinds of things that they would have, that they said that they wouldn't do only 10 years ago. And so I'm a little bit skeptical that, that there will be a universally accepted way of controlling AIs that are smarter than humans. On the other hand, I'm not too worried about AIs that are smarter than humans, because you should be mostly worried about beings like yourself. Why? Because those who are like yourself, they share goals with you. And whenever you share goals, you can do two things. You can either collaborate and achieve these goals together. So an extreme form of that would be love and marry and master life together. Or you can compete, and you can, and maybe there's only one schnitzel on the table, but this guy wants to eat the schnitzel, and this guy wants to eat the schnitzel, and now they have a goal conflict. And so an extreme form of a goal conflict would be war, and we have had many examples of that in the past. Now, the long-term protection of humans is that there won't be too many goal conflicts between super smart AIs and the humans, because they will not be interested in the schnitzel. And generally speaking, every being is mostly interested in beings like itself, because with those, it can either cooperate or compete. And that's the reason why most CEOs of most companies are mostly interested in other CEOs of similar companies with whom they are competing. And that's the reason why most 7-year-old girls are mostly interested in other 7-year-old girls, you know? And that's the reason why most frogs of a certain kind are mostly interested in other frogs of the same kind. And most of the super smart AIs of the future are going to be mostly interested in other super smart AIs of the future, and not so much in the frogs and in the humans. So there is there's a certain hope for long-term protection through lack of interest on the other side.
Since the next paper session will be started in about 10 minutes, so we don't have time for more questions. I saw so many of you have more questions to Professor Schmidhuber. You may ask him in person during the whole, in the next couple of days. So let's warmly thank Professor Schmidhuber for his inspiring talk again.